to look out in the space. All right. What do they teach you when you start learning about telescopes and looking out at stars? The first thing they teach you is don't point your telescope directly at the stars that you want to see. Do they teach you that? That's true. You know why? When you're trying to see distant stars, there's not a lot of light coming through, right? Very little light coming through. You're going to see faint objects. If I look directly at faint objects, what will happen? Where's the light going to focus? Sorry? On the cones. Very good. Are the cones any good in low light? Cones are useless. Can't sense any damn thing in low light. Right? It's the rods that would be required to actually see in very, very low light conditions. So if I want to see something that is extremely low lit, I want to not focus directly at it. I want to focus slightly away from it so the lens or the light actually falls on my rods, away from your fovea. And the minute it falls on the rods, then I should be able to perceive it and see it. Okay? Now the color vision, of course, we don't, even though we say that we have these three distinct kinds of cones, we don't actually see, red in certain areas of the image, green in certain other regions, and so on and so forth. We don't actually see separate colors, right? We still see a continuous range of colors, right? So we sense across this broad spectrum, okay? And the color we perceive is simply an integral of each type of cone that actually got activated by a specific wavelength of light falling on it. Okay? So if I look at actually the sensitivity, I'll come back to this in a second. If I look at the sensitivity of my cones, you would expect to see sensitivity curves that look like this. Okay? So the blue for blue receptors, green for green, and red for red, of course. If you see, they tend to overlap quite a bit. Right? So every photoreceptor is capable to a certain extent of sensing across the full spectrum of wavelengths. It's just that the amount of energy that they would actually collect is not the same. It varies. Okay? So whenever we see color, it's truly an integral across all these wavelengths, and that's the color that emerges. Right? And we would see it as a part of the continuous spectrum. Okay? Now, in general, each of the cones that we have, they do have a peak sensitivity at a particular wavelength. Right? It turns out for the red, it's 580 nanometers, for green, it's 540, and for blue, it's 450 nanometers. Okay? That's when we have the highest sensitivity. Everything outside of that, it decreases. Now, on the other hand, for the rods, you're not, there's a sensitivity curve across the entire spectrum. Okay? And it turns out that they typically tend to have the highest sensitivity around 550 nanometers. Okay? But they still have a full range across 380 to 770. Okay? Now for the perception process, there are several factors that play a role in how well we are able to see things. Okay? Contrast being the first one. Now, contrast is simply a relationship between the luminance of an object and the luminance of the background. Right? So, how much variation there is in the basic luminance of things in your visual sight. Okay? So, things that are obviously very dark and very bright will have the highest contrast, and we'll see them most clearly. Things that have very, very small variations in shades of color, we don't see them very well. Okay? So the contrast is an important factor in our ability to sense things. Size is another one. Right? Not the actual size of the object per se, but the size of the projection of an object onto the retina is what matters. So for example, I mean, if you're trying to look at a very, very small object, you put it through a bunch of lens systems and magnify it. As long as the projection is large enough on the retina, you will see just fine. You see all the details. Right? So it's the projection of the object on the retina that matters, on how well we are able to see the details of that object. Okay? And the other factor is time. Well, the visual system is purely photochemical. Right? So things that are moving very fast in time, events that are changing in time very fast, that do not allow sufficient interval between photochemical processes, we simply cannot sense them. Okay? So time is another factor. If you have a very bright object, it's going to provide a lot of light, it's going to flash very fast, yeah, we may be able to see it. A very dim object flashing at the same speed, just not enough time for us to collect all the energy and process it. Okay? So time is important for the visibility to work. Now, the basic facts about how the eyes are situated. The distance between the eyes is 6 centimeters. Now, when we study, so the question is, when you separate the eyes, what does that facilitate? The separation of 6 centimeters, what does it do? Depth perception, very good. How? Right. Very good. So, but what does that do? What does that do in order to help us do depth perception? I see two pictures, right? They're separated from each other by a certain distance, right? But what does that separation amount to? How does that help me get to depth? Very good, very good. So we are going to do triangulation in order to get back to depth information. But in raw terms, things that are close to you will separate out more than things that are further away from you. Right? So just by knowing that a particular point in space is projecting on both the eyes, right, on the retina, if I were to figure out how much they are separated by from an absolute point, let's say the optic axis, it can tell me if that object is closer or further than some other object that projects onto the retina. Okay? So again, it's giving us relative information. It gives us depth information from that standpoint. The separation is what we typically call or refer to as disparity. Right? And we'll come back and study this, how we actually use it for triangulation purposes as we talk further about stereo vision. But that's one of the reasons why we have eyes that are separated by a certain distance. Okay? The eyes are, of course, roughly about halfway down your head. The visual field that you actually see for each eye is quite interesting. For monocular vision, you get about 160 degrees width, 175 degrees in height. Okay? That's a fairly large visual field that we have. When you go out and buy a wide field lens, what's your visual field? How many of you are photographers here? Like to take pictures, cameras? What do you think is the visual field for a wide field lens? Oh, yes, well, fisheye, yeah. Now, fisheye is huge, right? Fisheye is almost 180 degrees. But for a wide field lens,